All right, so I'm going to be leaving at 10 a.m. for a trip into the city. And I'm going, yeah, so it's 10:45 right now, but in theory, I'm leaving at 10 a.m. for a trip to the city, and I'm going to be back in 4 hours. What time am I going to get back? 2? Yeah, again, not a trick question. Um, great. And so what this tells me as a mathematician is that 10 plus 4 is 2. Great. Love it. How about this one? I'm gonna leave for a 22 night cruise on Friday. What day of the week am I gonna get back? Saturday? Right. So if I leave on Friday and then 22 is 3 weeks and 1 day. And so 1, 2, 3 weeks. Ah, if anyone figures out how to turn this off, would greatly appreciate it. So 3 weeks and 1 day. And so I will return on Saturday. And so this tells me, as a mathematician, that 22 plus, nope. Wait, what's the, okay. 22, sorry. We don't have a fun equation for that one, but this is what that tells me as a mathematician. So like adding one more gives me Saturday. So let's consider this one. So 10 plus 4 equals 2, but it doesn't actually equals 2. So like when we're in base 10, 10 plus 4 is what? 14. The problem here is that we're working in this mindset where we're working with a 12-hour clock, right? So if you use 24-hour time, then 10 plus 4 is, well, indeed 14. But if I leave at 10 p.m. for a 4-hour trip, even if I use 24-hour time, I am still getting back at 2 a.m. So what's the deal there? All right, so I pre-wrote these, so we're going to scroll past our activities and talk about this. So this is all about congruences, where we've learned what modulo means. We've learned what modulo means. And now we're going to try and work in this mindset, where we're going to define that given, again, integers, a and b, we say that they are congruent modulo m, and we write this a with 3 equal signs, b, and then mod m. And we say that this is the case if a minus b is divisible by m. And so, for example, we have, let's see, as examples, notice that 16 mod 5 is going to be equivalent to 6. Wait, no, that's not correct. Yes, it is. 16 is equivalent to 6 mod 5. Well, I don't like the way that the book writes it. Okay. Sorry about that. Hold on. Let's figure out what that sign is in LaTeX. All right. And so this is just a fancy way of writing this number. Like we've talked about modulo, we've talked about remainder, we've talked about the division theorem. And so now this is kind of just standardizing this notation where they write this as a theorem, but we say that A is equivalent or congruent to B mod M. And this is just equivalently writing that A is equal to M times T plus B for some integer T, right? And we know this from the division theorem, where if we multiply some number and then we have to add a remainder to get to our number on the left-hand side, this formula should be familiar to us. So yeah, and so the other part of the theorem the book says is if A is congruent to R mod M, they put this part in parentheses. So if you want to put it in parentheses, that's okay. This to me also seems perfectly reasonable. So if A is equivalent to R mod M and R is between 0, ran out of space there, and M, then we say R is the remainder. They use upon division of A by M. And again, this shouldn't be new to us. So let's look at 16 and 6. Mod 5. So if we have 16 divided by 5 is 3, remainder 1. 1 plus 5 is indeed 6. And so we can write 16 as, so if we write 16 as 6 mod 5, that's okay, but it's just, we're not there yet. And so it's also congruent to 1 mod 5. And for me, it's helpful to kind of think of the modulo as like a clock, where this especially makes sense if I'm leaving at 10 a.m. for a 4-hour trip, and at 12 we reset. So after 12 we go back to 1. And mod is kind of like that, where we've got this clock that goes 0, 1, 2, 3, 4. And since we start counting at 0, we don't go up to 5. And so as we go through numbers, so like 1 on the modulo clock is 1, 2 is 2, and so on. And once we get to 5 is going to be back around to 0. 6 is going to put us up 1. 7 puts us at 2. 8 puts us at 3, and so on. Right? So we have this notion of like our clock hand going around, and just a different number of whatever our modulus is, that's the numbers of the clock. All right. One thing that the book doesn't have, but that may be useful to you is, so if we're working with this equation, A is congruent to B mod M, and you want to know what B is given A and the modulus, if you've got a calculator, then B is going to be equal to, well, so how do we figure this out? So if we've got, let's pick two numbers that I didn't plan ahead of time, 120 and 7. And so to figure out what the remainder is, we have to divide 120. So 120 mod 7. So we divide 120 by that. And I can't think on my feet. So 12 divided by 7 is 1. And then we've got 3 plus 2 is 5. So 5. And then we divide 7 into 50. 7. Yeah. And then that's 49. Remainder 1. And so our B is 1. So how do we find out the remainder without doing all of that work? Another way is to, if we have a calculator, then we can divide 120 by 7. So let's find a calculator. Calc. Okay, so 120 divided by 7. That gives us 17. And so then we know this because a calculator won't give us a remainder by itself. So we do 17, and then we have to find out just how off are we. And so we would do 17 times 7. So 17 times 7 equals 119. And so, and then we do 120 minus 119, and that gives us 1, right? So that's another way to find out what the remainder is. An equation of that is, so first we had A divided by M, but we didn't take the whole thing. We found the floor of that. And then, so that number, that would give us 17. So that's A divided by M, floor. And then we multiply that by our modulus. And then we subtracted that result from A. So A minus that product. And that's a way to get B. So just formalizing, like, that's what we compute. Again, this formula is not in your textbook, so could be wrong, but I don't think.
Stuff is going plus negative A a bad idea in this case? Like I couldn't.
If you plus negative A, that's the same thing, algebraically. Yeah, that's okay. All right. So now let's talk about some properties. So first we have our kind of standard reflexive, symmetric, transitive properties. And so for reflexive, we want to know that if we have one number, that's equivalent to the same number mod M, which, like, if we have 2 is equivalent to 2 mod 3. Yeah, obviously. So that's the reflexive property. The symmetric property is if A, so A is congruent to B mod M, if and only if, I'm going to run out of room, if and only if B is congruent to A mod M. So we can swap them around. And so this is true even if A equals B, so 2 equals 2 mod 3, we can swap them around, 2 equals 2 mod 3. If we have, let's use a different color, if we have 16 is congruent to 1 mod 5, 1 is congruent to 16 mod 5. And so the right-hand side isn't fully reduced, as you say, but it is true. Like when we're working in modulo 5, 16 is equivalent to 1 is equivalent to 16. That's the symmetric property, so we can switch them around. And then the transitive property is if we have A being congruent to B mod M and B is congruent to C, I ran out of room again, mod M, then we can say A is congruent to C mod M. And so let's consider 16 is congruent to 6 mod 5. And 6 is congruent to 1 mod 5. So, right, all three of those are just 1 at our modulus clock of 5. Then 16 is congruent to 1 mod 5. That's how we get there. We could also say we could choose 16, 11, 6, and 1. All of those are 1 modulo 5. And the transitive property gets us there. Questions so far? Great. Let's do something more interesting with these. All right, so this is theorem 7.15 if you're interested. And this theorem is all about what can we do with this. This is modulo arithmetic. And so we have, assuming that A is congruent to B mod M and C is congruent to D mod M, then we're going to add them together. So A plus C is congruent to B plus D mod M, and we can also subtract them. A minus C is congruent to B minus D mod M. So let's see. So let's choose 16, and 16 is congruent to 1 mod 5. And let's choose 3. And so that would be let's do 23 is congruent to 3 mod 5. And then if we wanted to know, let's swap them around. 23 plus 16, 23 minus 16. So we could do all of this math with a calculator or in our heads because they're small enough numbers. But if they were enormous numbers, then if we know their congruence, so 23 is equivalent to 3, that's equivalent to doing 3 plus 1 or 3 minus 1, which is 4 mod 5, and this is 2 mod 5. And so that makes the math a lot easier. So if we can find the congruence, then we don't have to do all that computation. All right, step 2. if A is equivalent to B mod M and C is equivalent to D mod M, then AC is equivalent to BD mod M, so we can multiply. And in particular, AC is congruent to BC mod M. I just want to go over the proof for this, like kind of sketch it out. And so this is, maybe I don't want to go over the proof. Okay, never mind. Okay, so let's look at 23 being equivalent to 3 mod 5 and 16 and 1. And so 23 times 16, that's a big number. Do I want to compute it? No. This is equivalent to 1, or if I read it in order, 3 times 1, which is 3. So that gives us that. And if we wanted to do 23 times 16, and we already know that 23 is congruent to 3. So this in our case is A, B, C, D. 23 times 16 is equivalent to 3 times 16. And you can see how, like, if we use AC as equivalent to BD, that gives us what we want, where we end up multiplying 3 by 16, and 16 is equivalent to 1, and so that makes the math work out. So hooray, we can multiply things. We can also cancel things out. So if we've got AC is congruent to BC mod, this particular example for some reason uses N. And the GCD of C and N is 1. Then A is congruent to B mod N. So we can cancel things out, which is nice. And then number 4, A is congruent to B mod. We're back to M. We'll add words. So if this is true, then A to the N is congruent to B to the N mod M. For any natural number. So we could square both sides, we could cube both sides, we could raise each side to whatever power we want, as long as it's positive, and then we're good to go. Questions on these properties? All right, yeah.
If we were to use property 3, how would we show work for that? Would we like draw an arrow to a section of GCD or like explain it instead?
You could say like GCD, this number is 1. And then proceed. All right, so now I will move my activities. Where my activity? Ah, what? No. I would like to move the page over here. There we go. All right, so let's look at this one. So I'll do the first one. And I've got these two large numbers that I really do not want to have to multiply. I would like to know instead, I want to know what this product is mod 14, but I don't want to have to do that work. So let's figure out which each of these numbers is mod 14. And so again, remember that B is equal to A time or A minus A mod M times M. And so 32517 divided by 14 is 2322 times 14. 2322 times 14 equals 32508. So this is 32508. And then 32517 minus 32508 is plus 2 plus 7, 9. So 32517 is equivalent to 9 mod 14. And now we can do 5328. Okay, so 5328 divided by 14. 5328 divided by 14 is 380 and change. So this is 380 times 14. 380 times 14 equals that. And our original number was 5328. And so 5328 minus 5320 is 8. And so now we can just multiply 9 times 8. So 9 times 8 is 72. And then 72 mod 14 is a little bit easier to do. And so, okay, let's actually do this. 72 divided by 14 is 5. 5 times 14 is 70. That's 2 off from 72. Okay, so in terms of how you would actually write this, like on the homework. So I don't necessarily need to see all the steps, but if you write something like this, where you've got the big number is congruent to this number mod M and this number mod M, and then you can say 9 times 8 equals 72 is congruent to 2 mod 14, and then this is our final answer. So I want to see like the intermediate steps, but I don't need to see all the math. All right. So we're going to take maybe 5 or so minutes. We've got one more example about digits, which is fun. So we'll come back maybe at 20 or so. And I have markers for you. And so we'll maybe for this time, I'll have you get in your neighbor groups and go to the board and talk about these problems. So A is find 2 to the 1000 mod 15. Don't multiply out 2 to the 1000. B is we've got 3 numbers that we multiply and subtract. And what's that? Mod 6. And then C is we've got N is 8, or sorry, N is 5 mod 8. And so I have this equation and I want to figure out what is that equation, mod 8. Any immediate questions before we get started? All right, go for it. Get in your groups. I will come around and distribute markers. Okay, so let me just tell you the answers and then you can verify. So 2 to the 1,000 is 1. I'm going to n, so this thing n mod 6 is also 1. And then this is going to be 6 mod 8. So I've given you the answers, but I haven't told you why. And so I might make this warm up for next time. So even if you know the answers, that's not the point. The point is to know why. All right, let's talk about this section is called divisibility rules, but I am giving this the very, very unofficial name, the digit theorem, which is let's let n be some number where we write the digits as n minus 1 and then so on and then a1 and a0. And so for example, if my n is equal to 1, 2, 3, 4, 5, I will use purple for this. A of n minus 1 is 1. A of 0 is 5. A of 1 is 4. And so you can see how we like label this 0, 1, 2, 3, 4. So A of 4 is 4. Sorry. A of 4 is 1. A of 3 is 2, and so on, right? We're numbering the digits. And we're writing it like this, where we write each digit next to each other, like we do with the normal huge number. So if if n is, let's say, 9999, my A of 0 is my A of 1, A of 2, and A of 3, where they're all the same thing. Is that way of writing a number clear so far? So let this number be, I need a verb in there, an n digit positive integer. I'll use int, where a naught is the number of units, so ones. A1 is the number of tens, and so on. Then we've got some fun rules. We'll say that n is congruent to, if we have a n minus 1 plus a sub n minus 2, and so on, plus a1 plus a0. This says something mod 3. This statement is saying, in plain words, that a number is congruent to the sum of its digits mod 3, which is also saying that like for 3, we've got 3 options, 0, 1, and 2, right? So we're going to sum all the digits, and that sum is going to be congruent to 0 mod 3, 1 mod 3, or 2 mod 3, right? Those are all of our options. And so this also says that, let's think about like the 0 case. So if we add all these digits up and we get 0, what does that tell you about the number and 3? Yeah, it's divisible. So yeah, so this is also saying that if the sum of a number's digits is divisible by 3, the number is divisible by 3. And so this is the case where this is congruent to 0 mod 3. All right, and then I wish I'd left more room. The second case of this theorem is we just replace a 9 with a 3, where it says the same sort of things of a number is congruent to the sum of its digits mod 9. And if the sum of digits is divisible by 9, the number itself is divisible by 9. So if 1 is mod 3, so 1 is mod 3, 2 is just the same thing, mod 9. Step 3 of this theorem, if we write n as congruent to -1 to the n minus 1 times a to the n minus 1 plus -1 to the n minus 2 times a to the n minus 2 plus so on and so forth, plus negative a sub 1 plus a sub 0 mod 11. So in mod 11 land, if we take, what's this saying? So we know that if we have -1 to the 1 is -1, -1 squared is 1, -1 cubed is -1, -1 to the 4th is 1. So it flips the sign. And so if we're adding all the digits, but with each digit, we assign it negative or +1. And so this is saying if we write this number in this way, so let's try and figure out how to write this in words. If we add the digits, but alternate negation, or alternate, so to write a number mod 11, we add the digits, but every other digit we negate. So let's do 99999 mod 11. So if we start from the right-hand side, because we know the right-hand side is positive, and so we have 9 plus -9 plus, how many do we have? 1, 2, 3, 4, 5. 3, 4, 5. We could also know which to start. We could start with the left hand first. We know that 5 minus 1 is 4. And so that tells us that this first 9 is not negative. And so 9, great news, this almost entirely cancels out. Okay, so that's nothing, that's nothing, that's 9 mod 11. Hooray, I didn't have to do all that math. All right, that's our mod 11 trick. And then our mod 4 trick. This is not nearly as intimidating as the other one notation-wise. So we take the last 2 digits and we multiply them together. And that tells us that number mod 4. So last 2 digits. And I hope it is apparent to you that like if we have a number that is like 0, 6, we don't multiply like the 0 times 6. It's just the last 2 digits that we have. And so we can figure out what 6 mod 4 is easily. So we don't need to use this rule. So let's choose a number that I didn't plan beforehand. 77. So 7 times 7 is 49. So it makes it a little bit easier for us. So 49 mod 4. 4 times 9 is 36. And well, 4 times 9 is like if we have 4 times 9 mod 4, there's a 4 there.
Oh,
Wait, that doesn't, hold on. No. Okay, so 49 mod 4. We don't want to, I was wrong. We don't want to keep going and figure out what 49 mod 4 is. Also 4 times 9. Sorry, I'm getting myself confused. Okay. 77 is equivalent to 49 mod 4. And so now we just want to figure out what 49 is. And so like, how does this reduce? So this might be, can I do this on a 4-function calculator? Yeah. And so here's where I might figure out like, what is 49? And so okay. Wait, hold on. Maybe I'm getting this wrong. No, I am getting this wrong. Okay, I am wrong. I think, yeah, I am getting this wrong. Okay, so this number, that's not a product. It's just like we literally take the last 2 numbers. And so 77 doesn't give us any nice things out of it, but if we have this huge long number, that's equivalent to 77 mod 4. And that we can plug into our 4-function calculator. So we just take those last 2 digits. And then our final, we're out of time, sorry. Our final thing, this is the last thing, is n is equivalent to a2, a1, a0. Mod 8, again, this is not a product where we take the last 3 digits of a very big long number, and that tells us its modulus. with regard to 8. All right, so I've got some fun problems that we'll start next time with. And thank you for coming. I will see you on Wednesday.